Hello everyone. Today we'll be discussing our project problem. Our problem demonstrates an application of sequences. To begin, our problem states, suppose a rabbit colony begins with one pair of adult rabbits. Assume that every pair of adult rabbits produces 2 offspring every month, one male and one female, and that the rabbits become adults at the age of 2 months and live forever. Let A sub n stand for the number of pairs of adult rabbits after n months have passed, assuming n is greater than or equal to 1. And let R sub n be the following sequence. R sub n is equal to A sub n plus 1 over A sub n, assuming n is greater than or equal to 1. So, assuming R sub n is convergent, find the limit L of the sequence. Then interpret your result in terms of the number of pair of adult rabbits present in the colony from 1 month to the next. Now, this is when n is big, but for instance, suppose some fellow asks you to find A of 1 million. Quite a tall order there, but suppose you trick him into divulging that A of 999,999 is equal to S. Give the man an immediate answer to his question, hee. So, to begin, let's establish some definitions. In the problem, n is the number of months that have passed by in the colony. Number of months. And A sub n was the number of adult rabbits in the colony at month n. Adult rabbits. And then we were given a ratio, R sub n. And you see R sub n was a sequence. It's the ratio of the number of adult rabbits in the next month, n plus 1, over A of n, which is the number of adult rabbits in the current month. So, with these definitions established, we can move on and we can take a look at the steps we'll follow in order to find a solution to our problem. So first, we're going to create a table, and we're going to store the value of A of n, or the number of adult rabbits per colony, in each month n. From this, after say 15 values of n, we'll gather a pattern, and we can probably see what R of n will look like. We can see what the sequence is approaching, if it approaches any value at all, which it does. And then we will obtain a limit based off of the table for R of n. This will be a rough estimate. To get an actual estimate, we're going to solve for the exact limit algebraically afterwards. And once we have this limit, we will use it to solve for A of 1 million.
So first we're going to start filling in this table, and before I start I want to point out that when an adult has a pair of offspring, their newborns are 0 months old, and it will take them 2 months to reach adulthood to where they can immediately start producing offspring. So they'll move from 0 month old to 1 month old to adult. So in the 0th month, where we're starting, there is 1 pair of adult rabbits, and they produce 1 pair of 0 month old offspring. Then we're going to move on to n equals 1 at the 1st month, and we'll have 1 pair of adults. The 0 month old offspring will move to 1 month old, and this pair of adult rabbits will have another pair of 0 month old offspring. Then at n equals 2, we're going to have 2 pairs of offspring, or adult rabbit offspring. This comes from this pair and this pair moving here. Then these 2 pairs of adult rabbits, they produce 2 pairs of 0 month old offspring. And this 0 month old offspring moves to here at 1 month. So at 3 months, we have 3 pairs of adult rabbits. And these 3 pairs of adult rabbits produce 3 pairs of 0 month old offspring. And these 2 from the month before come down to 1 month olds. At n equals 4, we now have 5 pairs of adult rabbits. This comes from these 3 here, and these 2 being added. And then these 3 go down to here, and these 5 pairs of adult rabbits produce 5 pairs of 0 month old offspring. Now, from here we can kind of start seeing that a pattern emerging, where this column is the same as this column, because adult rabbits always, the pairs of adult rabbits always produce the same amount of pairs of 0-month-old offspring. So these two columns should be the same. And this this column right here is the same pattern as these two, but it's moved down one, as you see, like the ones here, here, and here. So we can start filling in our table a little bit quickly after this point. So as I was filling in the columns that regard to the number of rabbits, I noticed a pattern emerge in each of them. And that pattern is, if you look at the number of rabbits in 1 month, that is equal to the sum of the number of rabbits in the 2 previous months. So for example, at n equals 2, this equals the sum of the number of rabbits in the 2 previous months. So 1 plus 1 equals 2. And this pattern continues in all 3 columns. So 1 plus 2 equals 3, 2 plus 3 equals 5, and so on. And this pattern is called the Fibonacci sequence, or the Fibonacci pattern, and we'll talk about that later. But now I want to calculate some r sub n values, and we know the equation r sub n equals a sub n plus 1 over a sub n. We got that in our project problem. And let's start filling in this column. So what this expression means is you take the number of adult rabbits in the month after the current month and divide that by the number of adult rabbits at the current month. So for n equals 0, r sub n will equal 1 divided by 1. So you get 1 here. At n equals 1, it will be 2 divided by 1. So 2. And then it's 3 divided by 2, 1.5. And then 5 divided by 3 is 1.6 repeating, and we can fill in the rest of the table using this equation. So after filling in the r sub n values, I noticed that these converge to about 1.618, so we know that the limit of r sub n is approximately 1.618, and now we're going to show you how to calculate this limit exactly.
Alright guys, as you can see from this table here, the adult pair gives you an interesting sequence. So let me draw it out right here. So a of n, the 0th term is 1, first term is also 1, and then 2, 3, 5. So the pattern here is the 0th term plus the first term give you the second term. And you can see a pattern as you move to the right. So 1 plus 2 equals 3, 2 plus 3 equals 5. So the thing is, you can infer that this a of n sequence equals to a of n minus 1 plus a of n minus 2. So let's use an example here. Let's say n equals 2. We plug in a of 2 equals a of 2 minus 1 plus a of 2 minus 2. So remember, a of 2 is 2. This gives you a of 1. A of 1 is 1. A of 0 is also 1. So this example works. But we're going to try another example. Let's say n equals 1. So we see that a of 1 equals a of 1 minus 1 plus a of 1 minus 2. Here's the dilemma here. So you get 1 equals 1. But what's a of negative 1? We don't have that. So this doesn't work. This tells us that the formula, the sequence only works if your n is greater or equal to 2. Alright guys, recall in the beginning, we said r sub n equals a sub n plus 1 over a sub n. So we want to get a nice formula for a sub n plus 1 using this formula we found here. So what we're going to do is let your n equals n plus 1. So if we plug in n plus 1 into n here, you get a sub n plus 1 equal to a sub n plus 1, don't forget the minus 1, plus a sub n plus 1 minus 2. So when you compute those out, you will end up with a sub n plus 1 equals a sub n plus a sub n minus 1. Okay, so we got the formula is n plus 1, a sub n plus 1 give you a sub n plus a sub n minus 1. So we're gonna replace this for a sub n plus 1 here. You would get a sub n plus a sub n minus 1 over a sub n. And you can go further as to write a sub n over a sub n plus a sub n minus 1 over a sub n, and that's the same as saying 1 plus a sub n minus 1 over a sub n. Okay. Once we get to this part, we can, for some reason, rewrite this as 1 over a sub n over a sub n minus n1. It's legal because you flipped it. And now we see something familiar close to this thing. So why is that so similar? Well, because if you let n equals n minus 1 for r sub n, you get r sub n minus 1, plug in your n minus 1 for your n values, and a sub n minus 1 plus 1 over a sub n minus 1. This would give you exactly a sub n over a sub n minus 1, which is exactly what we have here. So if you replace r sub n minus 1 with this value here, you would get 1 plus 1 over r sub n minus 1. So since we got this number 1 plus 1 over r sub n minus 1, we can connect it back to this value. R sub n equals 1 plus 1 over r sub n minus 1.
All right, so r of n approaches a limit. It converges as n gets big. Here from the table we got 1.618 approximately, but this is an approximate value. What we're going to do now is we're going to replace r of n with the exact limit here. And we don't have the actual value, but we can call it L. So we can say r of n is equal to L in this case. The limit approaches L, it converges to L. So therefore this equation can be rewritten as L is equal to 1 plus 1 over, we have Rn minus 1 here, but we can actually write L here as well because n is also approaching infinity anyway, so it doesn't really matter that you subtract 1 here. It's very trivial. So you also put L over here. So you have L equals 1 plus 1 over L. From here, we multiply both sides by L to get an equation. I'll show you right now. L times L, and the other side, L, 1 plus 1 over L. All right, so let's multiply this out. L squared right here. And then we have L plus L over L, which is 1. So L plus 1. Now, from here, we can get a polynomial function. We can get L squared minus L minus 1 is equal to 0. And we can get a value for L here by using the quadratic formula. So, in the quadratic formula, we have the template, x is equal to negative b plus or minus square root b squared minus 4ac all over 2a. And so we can tell from here that our a, which is the first value here, b and c, a is going to be 1, that's the coefficient here. A is equal to 1, b is equal to negative 1, and c is equal to negative 1. So let's solve the quadratic equation here.
Using this equation of quadratic formula and the values of each coefficient, so L squared has a coefficient of 1, L has a coefficient of -1, and it's just -1. So once you plug in b first, so negative b, which is negative over times -1 plus minus square root. -1 squared minus 4 times 1 times -1 all over 2 times 1. Okay, so now we got down to this part. You see that we have two solutions. You see the plus and minus. So let's do the plus first. So you go to the plus, you get 1 plus square root of 1 plus 4, 5 over 2. And then on the other side, you have the negative 1 minus square root of 5 over 2. Alright guys, now we want to compute these two numbers to find out which one's the correct number. So, if you compute this number, one momento, boop, 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 you get 1.61803, and this one should give you negative 0.61803. So which one do we want? Well, let's see. What number is our L? 1.618, which is a positive number that's exactly almost the same. So we take the L and call it a day.
So we've already established that L, our limit, is equal to 1 plus root 5 over 2. This is the limit of R of n as n approaches infinity. Now this is actually the golden ratio. Recall that R of n sub n is equal to A sub n plus 1 over A sub n. We can use this ratio to calculate the value of the number of adult rabbits in a colony with n big. Now with this in mind here, and our ratio in mind, we know that R of n is approximately 1 plus root 5 over 2. Now, we can get R of 999,999 and set it equal to A of 1,000,000, which is n plus 1, over A of the same value on the left right here. Now, this here is approximately equal to our ratio. And we saw here too that you have one value here and you have the next value, and putting the next value over the previous value gave you that ratio for all the other values with n large. So this would approximately be 1 plus root 5 over 2. Excuse me, root 5 over 2. And so now that we have this here, we can actually solve for A of 1,000,000. The problem told us that A of 999,999 is equal to S. All right, so now that we have this value right here, what we're going to do is we're going to cross multiply. So A of 1,000,000 times 2, and 1 plus root 5 times A of this value, which we considered S now. So let's cross multiply. And so A of 1,000,000 times 2, 2 times A of 1,000,000, or sorry, A sub 1,000,000. All right, you set that equal to S times 1 plus root 5. All right, this will give you, if you divide 2 on both sides, let's cross 2 out here, we get A of 1,000,000 is equal to 1 plus root 5, sorry, I put 2 there again, excuse me, 1, over 2 times S. We get this value.
So in conclusion, this problem displayed an application of the Fibonacci sequence in limits. The number of pairs of adult rabbits in a colony grew at a rate that could be estimated by the Fibonacci sequence for a certain month n. The ratio R sub n represents the golden ratio and has an application in our problem, whereby we can gather the number of pairs of adult rabbits for a large value of n, in our case n equals 1,000,000. Granted, this answer was given in terms of S.